What is fuzz testing? Fuzz testing is basically a kind of random testing, which is a kind of testing in which inputs for a test case are generated randomly or semi-randomly. The goal of fuzz testing is to make sure that bad things don't happen. By bad things, I mean crashes, such as due to memory errors or uncaught exceptions, or hangs due to non-termination. As we have seen, memory errors often correspond to exploitable vulnerabilities, and thus are security critical. Non-termination is also a security problem since it can create a denial of service. Now, these are not the only bad things, of course. For example, a program could produce the wrong output. But a fuzz tester doesn't know anything about what the outputs of his tests should be. The fuzz testing tool only knows that those tests should not hang or crash. As such, fuzz testing is a very useful but a very limited endeavor. It complements but does not replace traditional functional testing. In fact, functional tests can be the starting point for fuzz tests. Input from functional tests is assumed to be legitimate, and fuzz tests can therefore derive input from these legitimate tests.
There are three basic kinds of fuzzing. The first is black box fuzzing. In this case, the testing tool knows nothing about the program or its input format, and instead just generates random inputs to throw at that program. Now, this is very easy to use and to get started using, but in the end, it may explore only shallow states in the program unless it gets very lucky. Grammar-based fuzzing works by having the tool generate input informed by a grammar that describes the input format expected by the target program. Now, this is more work to use because the operator needs to define the grammar, but on the other hand, it will often go deeper in the program state space. In particular, a grammar-based fuzzer will be able to get past the well-formedness checks that the target program probably is implementing on its input, and therefore will be able to cover more parts of the program. The last kind of fuzzer is a white box fuzzer. In this case, the tool generates new inputs at least partially informed by the code of the target program itself. Now, these tools are often easy to use because the fuzzing tool itself is able to look at the code and decide what inputs to generate to go to different parts of that target program's code. But as a result, they can be computationally expensive because they'll involve things like theorem provers. There are different ways that fuzzing tools generate inputs to pass to the target program. The most common way is by mutation. In this case, the fuzzer takes a legal input provided by the operator and mutates it using that as an input instead. Such legal inputs might be human-produced or automated, for example from a grammar or SMT solver query. The mutation might also be forced to adhere to a grammar. Legal inputs are often borrowed from legitimate functional tests. The second way that inputs are produced is generational. In this case, the tool generates an input from scratch. It might do so entirely randomly, or it might do so following a grammar to the program. And there may be combinations of these. For example, we could generate an initial input, then mutate it n times, generate new inputs, mutate those, and so on. And of course, mutations could be generated according to a grammar too. That is, if the original program's input adheres to a grammar, then we create mutations to that input that are informed by that grammar to make sure that it is likely to get further into the program's state space. Now, there are two basic ways that fuzzers are used. One is as file-based fuzzers, and the other is as network-based fuzzers. So let's look at the file-based approach. What's going to happen here is the fuzzing tool will mutate or generate inputs. It will then run the target program using those inputs and see what happens. So here it is visualized. An example of a file-based fuzzer is Redamsa. Another one is Blab. Redamsa is a mutation-based black box fuzzer. It mutates inputs that are given, passing them along to the target program. So here's an interaction with Redamsa. We start by echoing a legal input, passing it to Redamsa. Redamsa's arguments include a random seed, as well as the number of random input mutations to generate. You can see here that the inputs that Radamsa produced are variations of the input it originally received. Now, Radamsa can sit in between the generation of normal inputs and the receiving target program as follows. Here we're showing that the original input, which is a legal arithmetic expression that we might pass to the calculator program BC, can have that input fuzzed by Radamsa first before BC is able to operate on it. Blab is a grammar-based fuzzer. The grammars are specified by the user as regular expressions and context-free grammars. So as an example, Blab would take a regular expression as a command line argument describing the legal input space, and using that regular expression, it can generate an input that can be fed to the target program. Another example of a file-based fuzzer is American Fuzzy Lop. It is a mutation-based white box fuzzer, and it works according to the following process. We begin by instrumenting the target program to gather runtime information. This is how it uses the code to determine what the next inputs ought to be to improve coverage. The instrumentation it inserts tracks tuples that indicate where the program's execution has taken it, and these tuples consist of the ID of the current code location, you can think of this as just the line number, and an ID of the last code location before reaching the current one. With the instrumented program in hand, we run a test, and we mutate the test input to create a new test if an unseen tuple was generated by that test. Otherwise, the test was not useful for covering new spaces of the program, and we simply discard it. Mutations consist of things like bit flips, arithmetic, and other standard sorts of things used by mutation-based fuzzers. After running for a while, American Fuzzy Lop will periodically cull the gathered tests to avoid getting stuck in local minima. In a sense, it will stop making small local changes to tests and instead make one big change to try to jump to a different part of the state space. So here's an example interaction. We can start by running AFL GCC. This is meant to be a drop-in replacement for the GCC C compiler. AFL GCC will instrument the target and pass it along to GCC for compilation. Using the instrumented target program, we call AFL Fuzz, and this starts the process of fuzz testing. This will run for a long time and produce diagnostics as it discovers failing tests. Another example of a white box fuzzer is Sage, and this uses symbolic execution as its underlying test generation technology. We talked about Sage in the prior unit on symbolic execution. Another kind of fuzzer is a network-based fuzzer. In one role, it can act as one half of a communicating pair, sending messages to and from a target program, trying to get it to crash. Inputs could be produced by replaying a previously recorded interaction and mutating it, or by producing an interaction from scratch, for example, from a protocol grammar. Here we can imagine the interaction specification being given to the fuzzer. The fuzzer can then interact with the target, mutating that interaction input until the target potentially crashes. Another role for a network-based fuzzer is to act as a man in the middle, mutating inputs exchanged between parties, again with those mutations possibly informed by a grammar. An example of a network-based fuzzer is Spike. Spike is a fuzzer creation kit, and it provides a C language API for programming fuzzers in C that interact with remote servers using network-based protocols. The way that a programmer uses Spike is to create a series of blocks that form parts of protocol messages and to leave holes in those blocks that Spike can fuzz. As an example, we might start off by specifying a size string call. This indicates that in the protocol, a length field for the rest of the packet will go here. We don't know what that length yet will be, so we leave a placeholder for it using size string. Next, we specify the start of the block whose length we're interested in, and we specify some contents of that block. If we want to insert constants, we can use the sString call. Here we use the string variable call, where the argument is a prefix of the fuzzed component. So user equal Bob will be included in the block, and then a bunch of random text will follow it. We end the block, and this will determine the length, which can get backpatched at the start. Spike then allows you to connect to a particular host and port via TCP, send the block, and then close the connection. Of course, there are many other examples and interactions that Spike permits. Another example network fuzzer is burp intruder. It's one element of the burp suite. Burp automates customized attacks against web applications, and it's similar to Spike in allowing the user to craft a template of a request but leave holes, which it calls payloads, for fuzzing by the tool. Unlike Spike, which is a programming API, Burp Intruder provides a nice GUI front end. And Burp Intruder integrates with the rest of the Burp suite, which includes a proxy, scanner, spider, and many other tools. Okay, so you've been penetration testing, you're using fuzzing, and a crash occurs. You have questions. For example, what is the root cause of the crash that the fuzzer found so that we can fix it? In order to figure this out, we might ask, is there a way to make the input smaller so that it's more understandable? Or are two or more crashes signaling what is effectively the same bug? That is, do they minimize to the same input so that when removing superfluous differences, they result in a crash? Some tools provide some assistance in answering these questions, for example, in trying to make the input smaller automatically. Sometimes, though, the operator needs to figure this out for himself. Another important question is whether a crash is security relevant. That is, does it signal the possibility of an exploitable vulnerability? Now, a crash due to dereferencing a null pointer is rarely exploitable, particularly when running a user-space program, but buffer overruns more often can be. Memory errors are particularly difficult to deal with after fuzzing because the effects of a memory error may occur well after the point at which it originally takes place. That is, if you overrun a buffer and scribble over some portion of memory, the program will not immediately crash. Only when that scribbled over memory is reused will the program go the wrong way. One way to make it so that crashes happen immediately upon overwriting buffers is to use address sanitizer. This is a tool that can instrument a program so that accesses to arrays check for overflows and use after free errors. Given your instrumented program, you can fuzz it, and if the program crashes with an ASAN signaled error, then you can start worrying about exploitability. You can do the same trick with other sorts of error checkers for the purposes of testing. For example, Valgrind memcheck is another way of looking for memory errors. We've discussed several example fuzzers so far and the basics of fuzzing overall, and there are yet more fuzzers that are available for use. For example, the CERT Basic Fuzzing Framework, or BFF, based in part on an earlier fuzzer, ZZUF, is freely available, and it has been used to find bugs in commonly used software like Adobe Reader, Flash Player, Apple's Preview and QuickTime, and many others. Sully is a fuzzing tool that provides lots of extras to manage the fuzzing process. In addition to the core technology of generating random inputs to find useful test cases, Sully will watch the network and methodically maintain records about what's happened, instrument and monitor the health of the target, capable of reverting to a known good state if things go awry, detecting, tracking, and categorizing detected faults, and even fuzzing in parallel if that's desired.
Let's summarize. Penetration testing aims to simulate deployment scenarios involving determined attackers. The goal is to see whether the penetration team can find exploitable vulnerabilities. If they can, they have provided evidence of true insecurity. On the other hand, the lack of penetrations is not evidence of their impossibility, and as such, designs should always aim to mitigate and recover from as yet unknown attacks. Pen testers employ a variety of tools in their work, ranging from scanners to proxies to exploit injection and management tools to fuzz testing tools. Nevertheless, tools are no replacement for an ingenious and thoughtful testing person. Such a tester will use tools to increase the coverage, speed, reliability, and repeatability of her efforts.